Okay, get ready to dive into something pretty fascinating. The science of light. We're looking at excerpts from a Chinese science lecture, and
Wow.
it's really got me thinking. It kind of takes this playful approach and asks,
Mm.
what if everything we thought we knew about light was totally wrong?
Yeah.
So we'll be blending history, science, and a little bit of
Yeah.
what if speculation.
It's always interesting to look back and see how people throughout history have tried to understand things, especially something as basic as light, right?
Origin.
This lecture really shows how even the smartest people can get things wrong when they start with the wrong assumptions.
You are so right about that. And speaking of assumptions, let's start with the ancient Greeks.
Okay.
They had some pretty, how should we say, unique ideas about how we see.
Right.
They thought our eyes actually emitted something
Ooh.
to feel the world around them. Almost like a superpower version of touch, you know?
It's like a sense of touch.
Yeah. Like, kind of like those scenes in movies where you see bats flying in the dark
Oh, yeah.
and they use echolocation.
Oh.
The Greeks thought our eyes were doing something similar, but with beams of sight instead of sound.
So instead of sound waves, they're beaming out sight waves.
Yes, beams of sight.
Gotcha.
Like little tiny laser pointers shooting out of our eyes. It's a funny image.
Yeah, definitely.
But you know what? This theory, even though it was wrong,
Mm-hmm.
it actually led them to some interesting ideas.
Oh, really?
You know, Euclid, the geometry guy,
Yeah.
he used this theory to explain why things appear smaller as they get farther away.
So using the wrong theory, they got some kind of right answers.
Oh, right.
That's interesting.
So he thought those sight beams were spreading out as they traveled,
Oh.
and that meant they covered a smaller area on distant objects.
I see. So like the beams are going out and they're getting
Wider.
wider and wider.
Yes, wider.
Okay.
It's kind of a clever explanation, even though the basic idea was off. But it does bring up a really interesting question, though.
What's that?
If light is coming from objects, how do our tiny little eyes capture enough of it
Yeah.
to see this whole vast world around us? I mean, it's like trying to catch a tidal wave in a teacup.
Yeah. Yeah. So that's a really good question.
And that is where Alhazen comes in.
Okay.
He was an 11th century scholar who's often called the father of optics.
Father optics.
This guy, he wasn't afraid to question the accepted wisdom,
Hmm?
and his critical thinking led to a huge breakthrough.
So what did he figure out?
So his big insight came from a pretty simple observation. Darkness exists.
Darkness exists.
He basically said if our eyes were always emitting something to see,
Right.
we wouldn't experience darkness at all.
That makes sense.
The fact that we do experience darkness means that light must be coming into our eyes from outside sources,
Okay.
not being sent out from them.
Gotcha. So we're receivers, not transmitter.
We're receivers of light.
It's so simple, but it's
simple.
kind of profound too.
It really changes how we think about vision. We're not beaming out light. We're catching these little photons bouncing off everything around us.
Like little ping pong balls bouncing around?
Yeah, like tiny little ping pong balls bouncing all over the place.
Wow.
And, you know, this brings up another interesting point.
What's that?
What are we actually seeing then? Alhazen realized that most of the stuff in the world,
Right.
it doesn't actually emit its own light. It's simply reflecting light from sources like the sun or lamps or our screens, which are basically just tons of tiny lamps packed together.
Like a whole bunch of little lamps.
Yeah, exactly.
Perfect for saying.
Makes you wonder, right? What if our world is secretly full of light that we can't even see?
Oh, wow.
Imagine a world that's as bioluminescent as Pandora from Avatar,
Right.
but we're blind to most of it because our eyes can only detect a limited range of the spectrum.
Limited range, yeah.
Like maybe there's this whole psychedelic light show happening all around us and we just can't perceive it.
That's really cool to think about.
It is.
It makes you wonder what's really out there
It does.
that we can't see.
Yeah, all these hidden worlds.
And it kind of leads us to this next big leap
Oh, wait.
in our understanding of light, which is Isaac Newton and his particle theory.
Oh, Newton, the apple guy, right?
Yeah, the apple guy.
The guy who supposedly had an apple fall on his head and then completely revolutionized physics.
That's the one.
So in his book, Optics, he proposed that light is made up of tiny little particles. He called them corpuscles.
Corpuscles, interesting.
I know, right? Sounds very scientific.
It does.
So it might seem pretty simple now,
Yeah.
but back then it was a radical idea. And this theory actually explained a lot about how light behaves.
Like what?
Like, take reflection, for example.
Okay.
Light bouncing off a mirror is kind of like a ball bouncing off a wall.
Makes sense.
And then there's refraction. The way light bends when it passes through water.
Oh, like when a straw looks broken in a glass of water.
Exactly.
Because it's bending at that point where the
Right.
air and water meet.
That's because the light is changing direction as it moves between those two different materials.
Interesting.
So you see, the particle theory had a lot going for it. It was neat. It made sense. But like all good scientific theories,
Yeah.
it eventually ran into a few things it couldn't quite explain.
Like what kind of thing?
Oh, stuff like, how come beams of light can pass through each other without colliding?
That's a good question.
If light's made of these little particles, shouldn't they be crashing into each other like tiny billiard balls?
Right. That's what you'd think, right?
Yeah, you'd think so.
It makes you wonder if light's a particle. Then
Right.
What else could it be?
So is light a particle, or is it something else? That's where things get really interesting.
I'm intrigued.
And that's where we'll pick things up next time.
I can't wait.
Okay, so last time we left off with this big question.
Yeah.
Is light a particle or something else? And I'm really ready to dive into this whole wave-particle duality thing.
Yeah.
Sounds like something out of a science fiction movie.
Yeah, it really challenged a lot of what physicists thought about the universe back in the early 1900s.
Right.
So basically, wave-particle duality means light can act like a wave, spreading out like, ripples in a pond, or it can be like a tiny little packet of energy, like a particle.
Okay, wait a second.
Yeah.
How can something be both a wave and a particle at the same time? That's like saying a cat can be both a fluffy feline and of Endy, a puddle of liquid fur at the same time.
Yeah.
Right. It doesn't make sense.
It does seem counterintuitive, doesn't it? But the evidence for it is really strong.
Yeah, okay.
The classic experiment that shows this is called the double slit experiment.
Double slit experiment.
So imagine you shine a light through two narrow slits.
Okay.
And if light was only made of particles, you'd expect to see two bright spots on a screen behind the slits, right?
Yeah, that makes sense.
Two slits.
Two slits.
Two beams of light particles hitting the screen. Simple.
Simple.
But that's not what happens. Instead, you get a pattern of bright and dark bands on the screen. It's called an interference pattern.
Interference pattern.
This is something you see with waves. It's like when two sets of water waves intersect and create areas where the waves are higher and lower.
So you're saying light is a wave then?
Well, based on that, it would seem so, wouldn't it?
Yeah.
But other experiments show light acting like a particle.
Really?
There's something called the photoelectric effect. Einstein actually helped explain this.
Wow.
It shows that light can knock electrons off a metal surface, which only makes sense if light is delivering energy in these little concentrated packets, like tiny bullets of energy.
So light is acting like a wave in one experiment and a particle in another. So which one is it, really?
Yeah. Well, that's the really strange part. It seems like it can be both. And it kind of depends on how we're looking at it. When we try to measure its wave-like properties, it acts like a wave. But when we measure its particle-like properties, it acts like a particle.
Are you saying that our observation, how we're looking at it, actually changes how light behaves?
That's right. That's a big part of quantum mechanics, the study of the very small. At this tiny level, things don't follow the same rules we see in our everyday lives. Things can exist in multiple states at once, and just observing something can determine which state we see.
So that's what they mean by quantum weirdness.
Exactly. It really challenges how we think about reality.
Okay, so light is this wave particle thing. What did that mean for us? What's the bigger picture here?
Well, for one thing, it means that what we call light is just a tiny sliver of a much bigger thing called the electromagnetic spectrum.
Okay.
There are all sorts of light waves out there that our eyes can't see: radio waves, microwaves, X-rays, gamma rays.
So we're surrounded by this whole world of light we're just oblivious to. It's like we're missing out on some giant cosmic light show, right?
That's a great way to put it. And some animals can actually see parts of this spectrum that we can't. For example, birds, reptiles, and insects can see ultraviolet light.
Oh, wow. Ultraviolet light.
It's just beyond the violet end of the visible spectrum.
I wonder what the world looks like to them. It must be like a super vibrant psychedelic version of what we see. Like, imagine what a flower garden looks like to a bee.
It probably looks incredible. Maybe they see patterns on flowers that we don't.
Right.
To attract pollinators or help them spot prey that's camouflaged to us. It gives them a whole other way of experiencing the world.
It's like a superpower. What other crazy vision abilities do animals have? I mean, besides the obvious ones, like eagles seeing things from miles away.
Well, there's some really amazing adaptations out there. Some deep-sea creatures can see bioluminescence, the light produced by living organisms.
Bioluminescence.
This is really important for them to communicate and survive in the pitch-black depth of the ocean. And then there's snakes, some of which can actually see heat. They have these special organs that allow them to sense infrared radiation.
Heat, like thermal vision.
Exactly. It allows them to detect warm-blooded prey, even in the dark.
Wow, snakes are even creepier than I thought. But what about us mammals? Why do we have such limited vision compared to some of our animal relatives?
Well, keep in mind that mammals evolved mostly during the nighttime,
Okay.
when color vision wasn't so important. A lot of mammals, like dogs and cats, are colorblind, or at least can't see as many colors as we can.
So it was an evolutionary trade-off.
Exactly. They traded a full spectrum of colors for better night vision.
We got to see better in the dark, but we lost the ability to see a super vibrant world. It makes you wonder what it would be like if we could see the full electromagnetic spectrum.
It's a fascinating thought experiment, right? But even with our limited range of visible light, there's a surprise that changes how we think about color perception.
A surprise.
It turns out that even when we're looking at the same wavelengths of light, we might not be seeing the same colors.
Wait, what? Are you saying that what I see as red might look different to you?
Yeah. A study back in 1992 found that the cells in our eyes that detect color, they come in different types. It's a bit like blood types.
Blood types for our eyes.
Yeah, kind of. These variations determine which specific wavelengths of light each cell is most sensitive to.
So even though we're all attuned to the same basic range of colors, there are small differences in how our cells interpret those wavelengths. That's pretty wild. So does that mean that someone's blue shirt might look a little purplish to one person and a little greenish to another?
Exactly. Or think about how some people might see faces as flushed or pale depending on their type of photoreceptor cells. It's interesting to think about how these subtle differences could affect how we see and experience the world.
But if everyone's seeing colors a little differently, wouldn't that make talking about color super confusing? Like imagine trying to describe a color to someone who sees it differently.
It's a good point. Luckily, these differences are usually pretty small and they're consistent within each person. So, while my red might be a bit different from yours, it's always going to be mammoy red. Each of us has our own consistent experience of color, even if there are small differences between people.
Phew. That's a relief. I thought we were going to have color chaos.
Right.
You know, you mentioned the sun earlier.
I did.
And I have to ask, what's the deal with sunlight? It seems pretty straightforward, you know.
Well, you might be surprised. We'll dig into the secrets of sunlight and the amazing journey those photons take to get to our eyes next time.
All right, we're back. And I'm definitely curious to hear about those sunlight secrets you mentioned.
Yeah.
I mean, it seems pretty basic, right? But with this lecture, I bet there's a lot more going on than we realize.
You're right about that. First off, did you know that most of the sun's energy doesn't actually reach us as light? It's crazy, but about 99% of it is radiated as something called neutrinos.
Neutrinos?
Yeah. They're these super tiny, almost ghost-like particles. They're incredibly hard to even detect.
Now that you mention it, I think we talked about neutrinos in the deep dive about dark matter.
Exactly. They're actually a top candidate for what makes up dark matter.
Oh, right. Dark matter, that mysterious stuff that supposedly makes up most of the universe's mass. We can't see it or feel it, but we know it's out there because of how it affects galaxies and stuff.
That's it. It's like this invisible web holding everything together. So the sun is constantly shooting out these neutrinos, and we're basically swimming in a sea of them without even knowing it.
Wow, it really makes you realize how much we don't know about the universe. It's like there are these whole layers of reality right in front of us that we're just starting to figure out.
Definitely.
Okay, so what about that 1% of the sun's energy that does reach us as light? We always hear it takes about 8 minutes for sunlight to travel from the sun to Earth.
Right, that's about right. It takes roughly 8 minutes for a single particle of light, a photon, to travel those 93 million miles. But here's the crazy part. That photon might have been created inside the sun, like over 100,000 years ago.
Wait, how is that even possible? If it takes 8 minutes to get here, how can a photon be that old?
Well, it's all because of how incredibly dense the sun's core is. That's where nuclear fusion is happening like crazy. Photons are constantly being created there, but they don't just shoot straight out. They bump into atoms, get absorbed, and re-emitted, bouncing around for thousands, even hundreds of thousands of years before they can escape the sun's interior.
So it's like this insanely complicated maze for these photons.
Exactly. It's a wild, chaotic trip. And the crazy thing is, the sunlight we're seeing right now is ancient. It's carrying information from a time way before they're even humans.
Wow, that's pretty mind-blowing. It's like each ray of sunlight connects us to these huge stretches of time and all the things that had to happen for that light to get here. But you know what's even more amazing to me? How our brains take those simple photons and create this whole visual experience of the world.
I know, right? Our visual system, with its 3 types of color receptors, is pretty basic compared to some animals. But then we have these powerful brains that take that limited visual input and build detailed, 3-dimensional images of everything around us.
It's like having a supercomputer hooked up to a regular keyboard. The hardware seems way too advanced for the software. It makes you wonder why we develop such big brains if our vision is relatively simple.
That's a huge question in science. Think about bats, for instance. They use echolocation to navigate tricky environments, all with a brain the size of a jelly bean. Why do WE need so much brain power, especially with our limited senses?
Maybe it's because we evolved to rely on complex social interactions, abstract thinking, and language. Perhaps our big brains are what really set us apart, letting us imagine, create, and explore the world in ways that other animals can't.
Those are great possibilities. It seems like our capacity for thought goes way beyond what we need just to survive. It really shows how limitations can sometimes lead to incredible adaptation.
Well, this deep dive into light has been eye-opening, to say the least. We've gone from ancient ideas about how we see to the weird world of quantum mechanics, from how we perceive colors to the epic journey of photons from the sun to us.
And we've touched on some big mysteries that still fascinate scientists. What is light, really? Why do we see colors the way we do? And why do we have these complex brains with our relatively simple vision?
Those are questions worth thinking about, and maybe they'll inspire you to learn more about the wonders of light and perception yourself. So keep looking up, keep asking questions, and never lose your sense of wonder about the universe we live in.